Hi everybody, welcome back. Today we're going to be working on the integral test and estimates of sums. Alright, so in the previous sections we were able to arrive at sequences and series, and we were able to show certain examples with those sequences and series as to how we are going to work with them. Alright, now in this particular case, what I want to do is I want to start introducing this sequence here, which is given by 1 over n squared. And this is going to begin at n is equal to 1, it's going to go towards infinity. And what I did here is I listed a few terms of that sequence. Alright, once I listed a few terms of that sequence, what I then did was I then said, hey, I want to plot this sequence, but I can't just plot it directly because I need some input and some output. So my input then just becomes my x values, and my output becomes the explicit formula that I was given here with this sequence. Now in that particular case, well then if I choose 1, well then 1, and then my first output is going to be 1. Secondly, my second term becomes 1/4, my third term is 1/9, my fourth term is 1/16, so on and so forth. Using those ordered pairs, I then plot the sequence, or these sequence of pairs, or these list of points given by 1, 1, 2 and 1/4, 3 and 1/9, 4 and 1/16. Alright, so this is what I'm observing now. I took this sequence and then I converted this sequence into ordered pairs. Now I'm doing this specifically so I can start analyzing what is this sequence doing. Alright, so far we get to see that the sequence is decreasing. Alright, all of these ordered pairs, all of these terms, the next term is smaller than the previous, and so on and so forth. So we can definitely see graphically that this sequence does seem to be decreasing. Okay, now what I want to do is I want to observe something else here. I now want to observe the series for the same explicit formula that I was given within my sequence. So what I want to do with that series, I then want to add every single term that was given to me. So I'm going to add 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, so on and so forth, all the way to infinity. But I want you to observe something. As I'm taking this interpretation for this specific series, notice that when I take all of the points that were in the previous list right up here, and I convert them into rectangles, notice that the area of each rectangle corresponds to each term in the series. Alright, well, how does that play out then? Well, what I want to do is I want to look at this length, or this width down here. This width, let's see if we can do this here. This width here is 1, and the height for this rectangle in here is a height of 1. So naturally the area here is 1. Okay, that's nice. But what about the next piece, the next rectangle? Well, the next rectangle, we know the height. The height was the y output, which was at 1/4. Well, what's its width? It's still just 1. So what's the area here? The area in this particular case is just 1/4. Alright, now we can keep doing this. Let's go with one more. Alright, just to get the nice fuzzy feeling. What's the height of that rectangle? Well, again, we know the height of the rectangle because that corresponds to the height of this point. In other words, the output for that y value, which means the area here is going to be 1/9. And like I was saying over here on this comment, the area of each individual rectangle corresponds to each individual term within that series. If I wanted to find the next area here for this fourth rectangle, then the area would just be 1/16. So in a sense, all I'm doing is I'm taking the summation of all of these individual rectangles. Okay, so that's a good graphical representation for what I have now. Alright, nice. Now I'm going to keep going. What I want to do now is, if you look at the bottom of your screen, what's going to happen if I then introduce the function of 1 over x squared? So here's that function, 1 over x squared. There we are. Now what I want you to do is notice all of these areas of the rectangles. All of the areas that we were initially observing up here for these rectangles now sit, or are now underneath, this function 1 over x squared. So I want you to now think about this. If we were to develop a, let's say, series such as this, and we were trying to determine, does this series converge? Well, one of the things that we know from the previous section is that we can use a comparison, right? We can use a comparison for these specific integrals, or sorry, for these specific series. But that's going to kind of now introduce us into this whole topic of how do we want to then pick them, and how do we want to know, or how do we determine if a certain, let's say, series diverges or it converges. Alright, so to illustrate this before we go through and set up the theorem, I want to go through and I want to dissect this example. This example here says, does the series for n beginning at 1 and going towards infinity of the explicit function of 1 over n squared converge or diverge? So here's that big question, does this converge or does it diverge? Alright, so that's where we want to, or sorry, that's what we then want to see. Alright, so what I'm going to do here is I'm going to base our work for this example on these pictures that we have listed here so far. Alright, so one of the first things that I want to do then is I want to start looking at the partial sum. So let's look at the partial sum S sub n. Now, the reason I want to look at the partial sum, if the partial sum is converging, then that probably means that my series is also converging. If the partial sum is diverging, meaning that every time I'm adding a new term and the sum just keeps getting larger and larger and larger, then that's going to mean that my series here is going to be diverging. So again, we want to look at that partial sum. So let's go through and let's start analyzing that partial sum. Alright, so I'm going to use here S sub n as my partial sum. And again, it's a natural occurrence that we always use that S sub n as a partial sum. Alright, and I'm only going to list out a few terms here for this series. There we are. And I'm going to go all the way to n squared. And again, this is my partial sum. Alright, so as I'm looking at this partial sum, again, partial just means that we get to some stopping point. And that stopping point is going to be 1 over n squared. Alright, or stopping point of n. So now what I want to do is I want to now start interpreting this partial sum. Well, like we did before, we're going to start looking at this series here. This series has a good graphical representation. More than that, each height of the rectangle has now a representation for this function. So what I want to do then is I want to now start comparing this. Alright, so I'm going to compare the series to an integral. Alright, well, what is that comparison going to be? Alright, So in here, I'm going to say that I'm going to take this series and I'm going to compare it to this function of the integral from 1 to infinity for 1 over x squared dx. All right, so we can see right on this last picture that that integral, right, from 1 to infinity will then get us a fairly decent approximation for this series. Now notice these two values are not equal to one another. All right, it's very, very important for us to carry that out. All right, so I'm just going to write a quick note right in here. Note. Whoa, ¿qué pasó? Nope. You did not do what I wanted. There we are. All right, good. So let's copy that over and let's put that right in here. Good. And then we're also going to copy this over. There we are. And I'll put it right in here. All right. It doesn't look too bad. All right. So let's move this right in. All right. So here we are. I'm just drawing this note really quickly. I'm going to change the color here. Let's go to red. There we go. Perfect. Oops. So note that the summation of the sequence, the summation of the series does not equal the integral from 1 to infinity for the same explicit function that we're looking at. And again, simply because we have this error right in here that the series is not accounting for. All right, so whether it be an over approximation or an under approximation, we're going to have that error. So in general, this does not work. All right, so in general, that doesn't work. All right, so it's important for us to just keep that on the back of our minds, that when we're finding this, whether this converges or diverges, it's not necessarily that they have the same sum, it's that they follow the same process for that end behavior of the sequence or that integral. All right, so good that I have all this now. So what I want to then extract here is I want to say with f of x being equal to 1 over x squared. All right, so now using my comparison that I had over here, or this partial sum that I was looking at, now I can then start saying this. Well, 1 over 1, we know that to just be my function here, evaluated at 1, right? Because that's what we were looking at right in here. It was the function being evaluated at 1. That was 1 over 1. The next one was the function evaluated at 2. The next term was the function evaluated at 3. Next term, the function evaluated at 4. Next term, function evaluated at 5. And we can keep going on with this whole process till we get to the very last term, our stopping point, which is going to be f sub n. Now, by the picture that we drew, well, we can now make a comparison. All right, well, what is that comparison now going to be? All right, well, let's start looking at that. All right, what I want here is I want to find all of these areas. All right, so what I'm going to do at this point in time is I'm going to say all of this here is less than, again, strictly less than because of how we define this function, f of 1 plus the integral from 1 to n, and this is going to be for 1 over x squared dx. All right, so this is what I'm looking at for this particular piece. All right, and again, all I'm doing here all I'm doing here is saying, okay, well, f of 1 is going to be the same, and then for the second piece, what I want is these areas underneath the curve are all going to be greater than the summation of all of these rectangles. Notice that's true because, again, we have this error that we are not accounting for, so therefore the integral will be larger in this particular case. All right, because again, we have all that error that we're missing. So this inequality still holds true. Awesome. Now, what I want to look at next, I want to look at this particular piece right in here. All right, the comparison that I'm going to make here is going to be this. That as I start looking at my integral, not just stopping at n, well, what if I send this off to infinity? That just means I'm going to add more terms onto this specific addition here. So what's going to happen here is that if I take my integral from 1 to infinity for 1 over x squared dx, this sum is going to be larger than this sum. All right, and it might be larger just by a smidge or just by some amount of error. It's still going to be larger. All right, so now we can go through and we can start working with this particular example. All right, so what do we now get from this? Well, let's start looking at this. See if we can evaluate this integral here. This integral is an improper integral, which we can evaluate. So let's go through that whole evaluation process. All right, so here we go. So now we can start saying, well, that integral, we know how to evaluate. That's just going to be the limit as, let's say, b goes towards infinity for the integral from for 1 to the power, or sorry, 1 to b. And this is going to be 1 over x squared dx. Now this just means that I need to go ahead and I need to evaluate that improper integral. So evaluating that improper integral, b goes towards infinity, that's going to be the integrand for 1 over x, and that's going to be a minus because I add 1 to that exponent, and this is going to be from 1 to b. There we are. Now what this gets us then, it's just going to be the limit as b goes towards infinity for, let's say, 1 over b, and then this is going to be minus and minus, so that's going to be a plus, and then that's going to be 1 over 1, so that's just 1. Now as b goes towards infinity, what happens to this first term? Well, that's just going to go to 0, so now we're just left with f of 1 plus 1. Which in this case, what is f of 1? Well, if we go back and if we start looking at f of 1 in this particular case is just going to be just 1. So this actually turns out to just be 1 plus 1. And in this particular case, it's just 2. Nice. So what we get here, so the conclusion here, if we follow all of this work, we get that the partial sum S sub n is actually less than 2. Nice. So what does that tell us about partial sums? Well, this means that the partial sum is bounded from above. So the partial sum is bounded from above. Well, what does that now tell us as this series is going to go off towards infinity? So that's going to tell us that our initial series that we were looking at for 1 over n squared converges. All right. Now that's going to be awesome. That's what we want to see, right? Whether a series converges or whether it's going to diverge. All right. Now, one of the important concepts or one of the important aspects to this is this analysis that we looked at up here. All right. So what I want to do is I want to take a moment to actually look at that analysis, right? So what I want to do here is I want to then start looking at this series. Is equal to 1 for this series. It's very, very counterintuitive, right? What I want you to do is I want you to look at what this series consists of. This series consists of all of these natural numbers just being added to one another, or sorry, not natural numbers, all of these rational numbers being added to one another. 1 plus 2 plus 3, or sorry, 1 plus 2, sorry, 1 plus 1 over 4 plus 1 divided by 9, so on and so forth. Now, adding all those rational numbers actually gets us an irrational number. This actually gets us, pi squared divided by 6. Now, I want you to compare that pi squared divided by 6 with this function that we used to approximate it, and that was the integral from 1 to infinity for 1 over x squared dx. This integral here actually got us a value of 1. So notice 1 is definitely not equal to pi squared divided by 6. All right, so we have to be very careful in that sense. Now, this is going to be a very important value that we get, and if I remember correctly, it was Leonhard Euler, that actually found this summation, and the proof of it is actually quite intense. You need some higher level mathematics to arrive at this conclusion that the series for 1 over n squared, where n begins at 1, is in fact equal to pi squared divided by 6. All right, so we're just going to kind of keep that in our back pocket for now. All right, but that's the introduction to this section. So now what I want to do is I want to now wrap this example up using the integral test. All right, so let's go through and let's define that integral test that we're going to be using for this particular section. All right, so here is our integral test. The integral test says that suppose f is a continuous positive decreasing function on an interval from 1 to infinity, and let a sub n be some explicit function, then the series for a sub n is convergent if and only if the improper integral from 1 to infinity for f of x dx is convergent. So, to summarize here, if we find that the integral for that function from 1 to infinity is convergent, then the series that we're comparing it to must also be convergent. If we get that the integral is divergent, then the series will also be divergent as well. All right, so this gives us a definite value to start, a definite purpose to start looking at some of these series in terms of integrals, because what we did back in chapter 7 is we developed a lot of integration techniques to figure out how this integration works. Now we start using all those integration techniques to say, hey, we can integrate these functions, and they're either going to diverge or they're going to converge. All right. So there are a few instances that, or a few, let's say, addendums that we're going to be looking at for the integral test. All right, so I'm just going to say these caution. All right, it's not in red because, again, it's not a full measure that I'm taking here. I'm just saying, hey, just be careful with this when this starts to occur. The series / integral does not need to start at 1. All right. Now, the integral test is defined for it to start at 1, however, does not need to start at 1. So just kind of keep that in mind. Does not need to start at 1. All right. The second caution that I want you guys to observe here is that the function f of x needs to decrease or let's say it needs to decrease for very large numbers. Now, what does that mean? Well, this basically means that you might find a function that doesn't start off decreasing right away, or doesn't decrease, it might be, let's say, constant, or it might be increasing just a little bit, and after a certain value, it starts to decrease. We want, so long as the end behavior, as we tend to infinity, then that portion of the function, or the series here, is then going to be decreasing. All right, so we just got to be very, very careful with that. And we're going to use Calc 1 to determine when is this function increasing, when is it decreasing. Once we're able to establish that, we just want to see, does the tail end, as we go to infinity, does that get very small? In other words, does it then converge? All right, so these small cautions are just kind of, hey, keep them in the back of your mind as you start looking at this, because we're going to keep on implementing this as we go through the rest of the course. All right, so now let's go ahead and let's try an example. All right, so here's the first example. We are to determine the convergence or divergence of this series. Now, this example is going to be for the series of n is equal to 1 to infinity for n times e to the power of negative n squared. All right, so what I'm going to do here is I'm actually going to use the integral test. And in order for me to use this integral test, I need to make sure that we meet these three criterias. All right, so we need to make sure we're continuous, positive, and decreasing. So just here in green, I'm going to write down what I'm going to need. All right, so I'm going to say here, use the integral test. All right, so one of the first things that we're going to have to check is the function continuous? Oops. One of the other requirements, we're going to have to make sure that our function is also positive. And lastly, that it needs to be decreasing. So we need to check out these three items for the integral test. Now, what I'm going to be using here for this integral test is going to be my function for f of x, which is going to be x times e to the negative x squared. Now, making some manipulation here using my algebraic techniques, this is going to be x divided by e to the power of x squared. So, we're going to have to then look at this specific function. All right, well, is it positive? And really quickly, I'm going to say for x greater than 1. All right, or sorry, x greater than or equal to 1, because our function for this series begins at 1. So in this particular case, is it positive? Yes. It will always be positive. The denominator always stays positive. The numerator, as long as it's greater than 1, greater than or equal to 1, will always stay positive. Is it continuous? All right, so is this function continuous? Yes, it is going to be continuous. Awesome. So far we have that the function is continuous and that it's positive. Now we need to check, is this going to be decreasing? All right, so let's go ahead and let's find out to see if this function is going to be decreasing. All right, so in order to see this, what I'm going to do here is I'm going to say use calculus. All right, so when you're checking this on the exam, I'll have a question that says show the 3 steps to determine that we can use the integral test. And that's all I want you to do, is show the 3 steps. Tell me that it's continuous by some process. All right, this is continuous because, again, the denominator is never going to be 0, therefore we never get items that are values that are out of the reach, and therefore does not provide any discontinuities. Positive is one of the easier ones to argue with, and then decreasing. In order to use decreasing, in order to determine when a function is decreasing, we're going to have to go ahead and use calculus, meaning we're going to have to take a derivative here. So I need to take this derivative, and that's exactly what I'm going to do. All right, I'm going to use a product rule here. So derivative up top, which is just going to be 1 multiplied by the second function, or the function at the bottom, minus the function up top, times the derivative of the bottom. The derivative of the bottom, this is going to be 2x times e to the power of x squared. And again, that's going to be using the chain rule here. And then this is going to be divided by the bottom squared, which is just going to be e to the power of x to the 4th. All right, not too bad. All right, it's looking pretty good. Now let's go ahead and factor an e to the power of x squared from that numerator. And naturally we're going to get 1 minus, let's see, that's going to be 2x, there we are, divided by e to the power of x to the 4th. There we go, not too bad. All right, simplifying this a little bit more, we should be able to get 1 minus 2x divided by e to the power of x squared. All right, it's looking good. E to the power of x squared. There we are. So all we need to do now is we need to determine when is this going to be increasing or decreasing. All right, so we're going to use our techniques back from calculus. So what I'm going to do is I'm going to use the first derivative test. All right, here's x, and I'm going to find out when my numerator and denominator are equal to 0. In other words, we're finding those critical values. So my denominator is never going to be 0, so that's nothing I need to worry about. But my numerator is 0. So my numerator is 0 whenever x is equal to 1/2. So that's exactly what I'm going to do, is I'm going to go here to x is equal to 1/2. All right, and then I'm going to pick some values. I'm going to pick a value to the left, and I'm going to pick a value to the right. So let's go through and let's pick those values. All right, say on the left I choose 0, and on the right I choose 1. All right, make some nice values here. So if it's 0, let's go to here, and we're going to get that this is positive, which means we are increasing from the interval from -infinity to 1/2. All right, it's looking good, and that should be inclusive. We can actually go exclusive here. All right, so let's choose a value of 1. If we go a value of 1, then this will actually get us negative, which means we are decreasing. And this is going to be decreasing from the interval from 1/2 to infinity. So is the value, or is the function decreasing beginning at 1 going towards infinity? Yes. And this here, we used the first derivative test. So using the first derivative test, we can then see, hey, we have this decreasing function, so great. We're able to make that assumption now. Right? So we now have this value to work with whenever we're talking about making these assumptions that these functions are going to be decreasing. And that's actually all that we need. All right, so continuous positive decreasing, awesome. All right, doesn't need to start at 1, but in our case it does start at 1, so that's awesome. All right, so next, what I want to do here is I want to then start using the integral. All right, so I'm going to be using the integral from 1 to infinity for my function, which is going to be x e to the power of -x squared dx. All right, I'm going to be using this specific integral to evaluate. So the integral from 1 to infinity, and then this is going to be x over e to the power of -x squared dx. All right. I can do a U-substitution here. So if we let U is equal to, let's say, negative x squared, then that means du is going to be to negative 2x dx, which means x dx is equal to negative 1/2 du. All right, it's looking pretty, oh, excuse me, sorry. I didn't quite catch that. There is no negative there, specifically because we eliminated the negative value. There we are, once we took it to the denominator. My apologies there. All right, so there we are. All right, everything's looking good, which now means that we have the integral, and the x dx becomes 1/2 du. So that's going to be 1/2, and this is 1 over e to the power of u, and this is going to be du. Now let's look at my bounds for integration. All right, so I'm going to look at two bounds for integration. One where x is tending towards infinity, and the other one where x is 1. So if x is 1, then we naturally get u is equal to 1. If x goes towards infinity, x squared, in this case u, will also be heading towards infinity. So my substitution still holds that my bounds are still going to be from 1 to infinity. Alright, so that's not too bad. Now this is an improper integral, so I'm going to go ahead and I'm going to evaluate it using the techniques that we learned back in the previous sections, back in chapter 7. Alright, so here's what we have so far. Now this is going to be 1/2 multiplied by, and this is going to be negative e to the power of negative u. Oops, I forgot my limit there. Limit as b goes towards infinity, and this is going to be for this integral, which is going to be negative e to the power of negative u, and that's going to be from 1 to b, which means this is just 1/2 multiplied by the limit as b goes towards infinity, and this is going to be for negative e to the negative b, and then this is going to be plus e to the power of negative 1. All right, looking pretty good. Now for this first term as b goes towards infinity, this is going to go down to 0, which then means that we're going to be left with 1/2 times e to the power of negative 1, which is just 1 over 2e. Now this does not mean that my series evaluates to this sum. This just means that this integral is converging. So to summarize, since, the integral from 1 to infinity for x e to the negative x squared dx converges, I'm going to say so does the series from n is equal to 1, n e to the negative n squared, so does this series. And this is by using the integral test. There we are. So this is how we use the integral test. If we can find that the series is going to converge, if we can find that the integral converges for the comparison that we're using for this series, then that's going to be awesome, because then the series is then going to converge as well. All right. So we must be able to use those two values in conjunction, or those two, let's say, those two methods in conjunction with one another. All right. Let's do part B. All right, so working with part B, we're going to say here that this is going to be the series from n is equal to 1, and this is going to be for 1 over 2 to the power of natural log of n. There we are. So again, we have to check those three conditions, all right, if we're going to use the integral test. So I'm going to say integral test we need three things. Number one, is it continuous? Number two, is it positive? And number three, is it is it decreasing? All right, so let's go through and let's check this then. All right, now the value that I'm going to be using, I'm going to say use f of x as 1 over 2 to the power of natural log of x. All right, that's the function that I'm looking at. So is this function continuous? All right, well, my apologies, and this is going to be for x is greater than or equal to 1. And again, because we're starting our series at 1, so this function is going to be defined for x is equal to 1 or larger. So beginning at x is equal to 1, then we here get naturally 0. All right, so that's not too bad. All right, that's not going to be too bad. Anything larger than that, it's definitely going to get us that this is continuous. So that's awesome. Is it positive? Yeah, sure it is. Even if the exponent turns out to be negative for some reason, this will always remain positive, so that's not too bad. Now, we're going to go ahead and we're going to use calculus to determine, is this function increasing or decreasing? All right, if it's increasing, we just stop there and we can't use the integral test. All right, so let's go through and let's use the derivative. All right, so I'm going to go on here to f prime. All right, so I'm going to use here, let's see, how do I want to do this? 2 to the power of natural log of x. All right, so for this derivative here, what I'm going to do is I'm going to use this value that I have here, or the derivatives that we learned back in chapter 6, times the natural log of a, and this is going to be multiplied by du dx. There we are. All right, so when I want to take this derivative, I got to account for the chain rule process to see what we're going to be able to extract here. All right, so let's go through this. All right, so my first derivative when I start looking at this, so this is going to be, in this particular case, 2 to the power of negative natural log of x, that's this first piece, multiplied by the natural log of 2, and then multiplied by the derivative of the numerator, derivative of the exponent. The derivative of the exponent is negative 1 over x. All right, so let's clean all this up. Let's make it look nice. All right, this is going to be negative, and this is going to be the natural log of 2 divided by 2 to the power of natural log of x, and I still have a multiplication by x. There we are. So what we then need to worry about in this particular case here is we then need to figure out, where is my numerator 0, where's my denominator 0? All right, those are the two things that we have to worry about in order to do the first derivative test. All right, again, you're trying to find those critical values in order for us to be able to determine what are these intervals. Natural log of 2, that's a constant. All right, 2 times natural log of x, 2 to the power of natural log of x. This never gets me 0. It's an exponential function. And then this one here, this one does get me 0 whenever x is 0. So I come here, x is 0. Now I need to figure out when it's increasing or decreasing. All right, so I need to pick values to the left and values to the right. All right, now for us, for the domain of this function, or at least in this particular case, this one up here too, that the domain of that function has to be from 0 going towards infinity, which means we can't choose any values to the left. So that's kind of nice. So all I have to do is choose a value to the right and see what's happening here. All right, so a value to the right, pick anything you want. So we can go with 1 and plug in the value of 1. So this is going to be 2 to the power of 1. That's just, 2 to the power of natural log of 1. Natural log of 1 is 0. So 2 to the power of 0 is just 1. But x is 1, so it's just 1 times 1. But then there's a negative out here, which means this is going to be negative. In other words, we are decreasing. Nice. So on the interval for where x is greater than 1, that means this function is going to be decreasing. Awesome. So now that we have this, I need to go through the integral calculations. So now I'm going to use the integral from 1 to infinity for this function of 1 over 2 times natural log of x, and this is going to be dx. There we are. All right, doesn't look too bad right now. All right, so what I'm going to do is I'm going to use a substitution here. So let's go with the substitution. I'm going to use u is going to be the natural log of x, and that means du is going to be, or actually, I want to, gotcha. I think I see where we need to go here. All right, so if u is equal to the natural log of x, gotcha. I see where I'm going. Then what I naturally want from here is I'm going to use an exponential here, so I'm going to say e to the power of u is equal to x in this particular case. And therefore, when I start looking at dx is just going to be e to the u du. All right, not too bad. All right, so once I have this, now I can go through and I can go back here to my substitution values that I'm going to initially look at, because dx can now be thought of as e to the u. So my dx is now e to the u du. That's my dx. And now 1 over 2 to the power of natural log of x, that's just 2 to the power of u. All right, so there we are. Everything's looking pretty good there. Secondly, what I want to do is I want to change my limits of integration. All right, so let's go ahead and let's change these limits of integration, because one goes to 1, the other one goes towards infinity. So I'm able to then extract that. So let's see, I'm going to go here. So one of the first ones is going to be u is equal to 1, and then the other one is going, oops, sorry, not u is equal to 1. My apologies. The first one's going to be x is equal to 1, so x is equal to 1. X is equal to 1 gets us that u, if x is 1, that means u is 0, and x is going to go to infinity. So as x goes to infinity for this natural log just keeps on increasing, which means u is going to go towards infinity. So my limits of integration now change from 0 to infinity. All right, not too bad. All right, everything's looking pretty good here. Next, this is now going to be equal to 0, the integral from 0 to infinity. And what I'm going to do is I'm going to factor out that exponent of u, simply because e and 2 are just constants, which means I'm only integrating this constant raised to this exponential. All right, so the way I'm going to do this is I'm first going to treat this improper integral correctly. There we are. To the power of u du. There we go. And all I have to do now is go through the whole evaluation process. All right, so find this integral here, and again, I'm just doing the antiderivative of this piece at the top right hand of your screen. I'm just doing the antiderivative there to figure out what I need to get here. So this is going to be the limit as b goes towards infinity, and this is going to be for 1 over, oops, excuse me, 1 over the natural log of e divided by 2. This is going to be multiplied by e to the power of 2 times b minus 1. There we are. So in this particular case, as we start looking at this and if we start evaluating, if we send b off to infinity, sending b off to infinity, well, that kind of keeps making this larger and larger and larger and larger and larger. Dividing by a constant, that constant is never going to change. Subtracting by 1, never going to change. That means this is going to go off to infinity. What does that tell us about the series then? Well, since, there we go. Since the integral from 1 to infinity for 1 over 2 to the power of natural log of x dx diverges, so does the series beginning at 1 for 1 over 2 natural log of n. So the series diverges. Awesome. And it diverges because, again, we use that we use that integral test. All right, awesome. So let's move on to the last part for estimating. All right, so we want to make sure that we find some bounds for these estimates that we're going to be observing. Or actually, give me one quick second. I forgot to talk about the p-series. So we're going to talk about the p-series not rather quickly, but we're going to talk about that p-series. So let's talk about the p-series really quickly. All right, this is going to be in blue. So the p-series and this is going to be the summation, and beginning at 1 for 1 over n to the power of p. This is going to be convergent if p is greater than 1, and divergent if p is less than or equal to 1. All right, so this is going to be very, very beneficial to us. All right, it's beneficial in the sense that we now start looking at these series in terms of a p-series. If I can find a p-series and if I can identify that I have a p-series, I will then be able to justify whether it will be convergent or whether it be divergent. All right, notice if p is equal to 1, then we have the harmonic series, and we know the harmonic series, that one is divergent. All right, so we then now have these different tools at our disposal, this tool being one of them. All right, I'm actually going to box this one in red because this is a super duper uber important process that we need to know, which is the p-series. All right, so what I'm going to do now is I'm going to use an example that has the p-series involved in it. All right, so let's go through. All right, so here we want to determine whether the series is convergent or divergent. And this series that I have here is the series that starts at 1, and then we add 1 over 2 root 2, and then we add 1 over 3 root 3, so on and so forth, all the way to infinity, because again, we just have dot, dot, dot. So what I'm going to do here is I'm going to try to determine if this is convergent or divergent, and one of the things that I want to do first is I want to try to get an explicit formula for this. So that's going to be the first thing that I want to observe. So I want to say here that I want to take the summation and beginning at 1, and then I see some sort of pattern here. All of the numerators have 1, so that formula is going to have 1. Denominator, it looks like it's 1 root 1. Denominator is 2 root 2, 3 root 3. So it kind of looks like it's n square root of n so far. All right. Now this I can express differently because they have the same base. I can express this as 1 over, let's say, n to the power of, this is 1 and this is a half, so 1 plus 1 half, that's going to be 3 halves. There we are. And this right here, this is a p-series. So I'm going to say this, the sequence, or the series, is a p-series, with p being equal to 3 halves. Now, what does that then tell us? Well, we then have to remember, well then p is equal to 3 halves, anything greater than 1 is going to be convergent. So what do we know about this series then? It converges. So the series converges by use of the p-series. And that's it. That's all there is to that. All right. So, not too bad. So the p-series, it's very, very powerful, and we do use it a lot, but one of the things that we always have to remember is, can we extract that p-series? Awesome. So let's go on to the last part of this section, which is going to be the estimate for these sums. All right, so I'm going to write up that estimate definition or that theorem really quick. All right, so here's the remainder estimate for the integral test. So we're going to have here that suppose we have some explicitly defined function where that function is going to be continuous, positive, decreasing function. All right, again, continuous, positive, and decreasing, those are all checks that we have to make to use the integral test. And this is saying for x greater than or equal to some n value. The n value, again, is where we typically start our series. And the series is convergent. All right, so if we've determined that the series is convergent, awesome. Then what we're going to do is we're going to define, or we're going to be looking at the remainder. All right, this is the remainder of that series that we're trying to find. All right, here, this is going to be the total sum. All right, so this is total series sum, and this is going to be the partial sum here. And this here is your remainder. Meaning that if we have the total series and we only calculate the partial sum, then that means we still have some part of the series that we haven't calculated. That's what we call the remainder. All right. Now, if that's the case, then we can bound that remainder using these two integrals. All right. Now, one important aspect of this is that once we have this remainder, one of the things that we can do, s minus s sub n, one of the things that we can do here is take all of these remainders and add the partial sums to them. Therefore, we get the series. Now, what happens then if we do that? What happens if we do this to our bound that we have for the remainder? Well, if that happens for the remainder, let's see, this is going to be the integral from n plus 1 to infinity for this function f of x dx, and this is going, oops, let me leave a space here, and then this is going to be the integral for n to infinity for f of x dx. There we are. And what I'm going to do is I'm going to add the partial sum to both sides. So I'm going to say, hey, I want to take the partial sum and add it to my bounds here. Therefore, what I have, what the result is now, is that I have this partial sum plus this lower bound, whatever this lower bound may be, dx, is going to be less than or equal to r of n plus s of n. That's just going to be the whole series. Which means we can find the series bounds just by knowing the remainder bounds. All right, now this is huge for us. All right, this is going to be huge. Now I'm just going to move this over a little bit here. There we are. All right. And actually, it didn't take that well. It's okay. Let's try it again. There we go. That looks way better. All right. So I'm going to have s sub n here. Oh, sorry. Cheese and crackers. It's okay. I'll just change the color here. There we are. All right. And then I want a plus. There we are. So this is what I'm looking at right in here. Now, again, this is a very powerful result that we are going to be using, and we're going to be implementing this in the next example. All right. So what I have for you all here is this example coming up that says I want to estimate the sum of the series excuse me, for n is equal to 1, and that's for 1 over n squared, using this inequality here. All right, so I'm going to say using, and then let's go ahead and let's bound this. It's okay. All right, so what I'm going to do is I'm going to use this formula here. So let's go ahead and let's copy that, and I'm going to put it right in here. There we are. Look at that. It's looking good. All right, let's paint it black. There we are. It's like seeing a red door. You just want to paint it black. All right. There we are, towards infinity. All right, awesome. So using this inequality, and n is equal to 10. There we are. So this is what we want to do. We want to estimate the sum of this series using this inequality that we just developed, and the value of n is equal to 10. Awesome. So one of the first things that I want to do then is I want to calculate these integrals. So that's what I'm going to look at first. So I'm going to look at the integral from 1 to infinity. All right, from 1 to infinity, and this is going to be for 1 over x squared dx. All right, so looking at this particular integral, again, it's an improper integral, so I want to make sure I evaluate it using methods for improper integrals. Now, when you're doing this on an exam, you have to then go ahead and state or show me here that you're evaluating these improper integrals correctly. All right, limit as b goes towards infinity, and this is going to be for 1 over x, and this is 1 to b. All right, and then this should be actually quite nice in this particular case. Actually, give me 1 second. My sincerest apologies, everybody. I'm actually using this integral here. There we are. Simply because I'm looking for this upper bound, right? I'm looking for that integral for that upper bound first. Now, finding this, this is now going to be the limit as b goes towards infinity for negative 1 over b, and then this is going to be plus 1 over n. But that first piece, that first term goes to 0, which means we're only left with 1 over n. All right, now that's not too bad. And notice I only did this one integral because now I can extract that if I did the other integral beginning at n plus 1 going towards infinity, then the same work is going to happen. The only thing that's going to be different is the end, which is going to say this needs to be, wow, this needs to be 1 over n plus 1. All right, so not too bad. All right, so let's go ahead and let's start using this sum here. All right, so I'm going to have s sub n. All right, I'm going to have s sub n plus the integral for n plus 1 to infinity for f of x dx less than or equal to this series, the total series sum, and then bounded by s sub n plus the integral from n to infinity for f of x dx. Now, we technically just found these two integrals, so I'm going to use my n value. Remember, n is equal to 10 from the very beginning, plus this integral here is this 1 over, and this is going to be 10 plus 1. All right, because again, it's n plus 1, less than or equal to s, less than or equal to, less than or equal to s sub n, which is in this case s sub 10, the partial sum. And then this integral was the one that we just found the very first time, which is 1 over n. There we are. And since n is 10, I'm going to use n being 10. So this inequality now turns into this value here, and that's not too bad. All right. Now all we need to do is we need to find these partial sums. So this in here, I'm going to circle these two partial sums, and I'm going to say S sub 10 is a partial sum. So that means to find this partial sum, I need to go through and I need to find out what that is. All right. That means I'm going to add the first 10 terms. All right. So let's see what adding the first 10 terms looks like. That's going to be 1 plus the second term, n is equal to 2. All right. So that's going to be 1/4. N is equal to 3. That's 1/9. And then we're going to keep on going all the way to the 10th term. All right. So that's 1 over 100, if I'm not mistaken, because the 10th term is going to be n squared, so n squared is 100. So this is the sum of the first 10 terms. Okay, now I'm going to put 10 terms. There we are. So the sum of the first 10 terms. All right, so let's go ahead and let's get an approximation here, because that's going to be as best as we can do. So this approximation I'm going to get for 1.54977 as my approximation, which now means that I can go over to this piece, my inequality, and start inserting what I know. Well, the first partial sum, that was what, 1.54977 plus 1 over 11 is less than or equal to the total series sum, and then here 1.54977 plus 1 over 10. Now, getting this addition, or making sure that we add this together, we're going to get for the lower bound of 1.64068 is less than or equal to the series sum, which is less than 1.64977. All right. Now, what does this tell us? Well, this again tells us that if I want to find the sum for this series, the sum has to be between these two numbers. Now, remember at the very, very beginning of the lesson today, I gave you all this sum. I said Leonard Euler found this sum, and it turned out to be pi halves over 6. Now, what is pi halves over 6? Well, let's go find out. All right, so let's go with pi squared divided by 6. So here I'm going to do pi squared, and then I'm going to divide that by 6. Hit enter, and I get 1.64493 approximately. All right, not too bad. So let's go ahead and let's write that down, and let's move on over back to the class. All right, here we are, which means this approximation is that 1.64493. Nice. So now look at these approximations. Now this works out really well. It actually is bounded in between there. So that is bounded in between, which is going to be really, really nice. And again, very counterintuitive to say that if we looked at the integral for this, the integral for this explicit function from 1 to infinity is actually 1. But when we do the series calculation for it, it's actually pi squared divided by 6. So again, in general, the series is not equal to the integral for the same function. All right, so we must always observe that. All right, so I hope you all enjoyed this lesson, and I will see you all for the next one.